Hi, good evening. I'm going to be talking to you about the interface between aerospace medicine and engineering. Thank you for the invite to talk. I'm very pleased to be involved with the next generation of aerospace medicine and hope you find this talk useful and interesting. And if you'd like to get in touch, I've included my email address there. And also, as I'm sure you're probably all aware now, it's a very active aerospace medicine community on Twitter. So another way to find out more about it is to follow me there and many of the other people that you already be hearing from in this series as well. In terms of what I'll talk about, I'll give you a little bit of my background, how I've ended up where I am and what I do, and then a little bit about my approach to the broader field, and then focusing in on how that relates to this particular topic area. I then go through some example projects and where I've been involved with interactions between medicine, engineering in the context of both aviation and space, and look a little bit in terms of future directions as well. So my background, medical school to start with at Edinburgh, and partway through that I was looking for different ways to get involved in extreme environment physiology and medicine, and more specifically aviation and space medicine. And I attended a conference symposium organised by Kevin Fong and Simon Ebbets back in 1999 about the future of space biomedicine in the UK. And I strongly encourage you to get out there and network. I mean, Next Generation Aerospace Medicine group will be a great way to do that. There's also lots of other symposia, conferences, in person or online, that you can go to at the moment. And it really is the way to find out about what you might be interested in doing in future, but also to speak to people doing the jobs that you might like to do, and to try and find ways to open the doors to get into those things. And Simon Ebbets at that time was doing a PhD with Professor John Ernsting, who ran the Human Applied Physiology Masters at King's, and so I got chatting to them through that route. Ended up doing the Human Applied Physiology Masters, which was run alongside the Diploma in Aviation Medicine. And so I got exposed to this specialty that we'd had nothing on it at medical school at that point, and it really opened my eyes to the world of possibility, and has been the track that I've followed ever since, really. So I joined the Royal Air Force off the back of that, did general RAF medical officer training and duties, including station time up at RAF Kinloss, and core medical training to get membership of the Royal College of Physicians. And then 2009 came back to King's to do the Diploma in Aviation Medicine course, and also was selected at that point to start training in aviation medicine, as it was at that time, and joined the Royal College of Physicians Specialty Advisory Committee, where we worked over the subsequent number of years to get this recognised by the General Medical Council as a specialty in its own right. And along the way, we managed to add in that it should be space, as we're looking to the future, not just aviation. Hence, we have the specialty of aviation and space medicine. Now in the UK, it was recognised by the General Medical Council back in 2016. Along the way, I then trialled the draft training curriculum with time with the Royal Air Force, the Civil Aviation Authority, over with the US Air Force, and also with the European Space Agency, and a variety of other industrial attachments around the UK as well, to give me a full breadth across the specialty. I also managed to do a PhD as part of that, looking at the effect of hypoxia on helicopter aircrew and the test and development of a portable oxygen delivery system for them. And that was very illuminating in terms of how physiologists and medical people are similar or different from a scientific or a clinical perspective, but also then how culturally and language wise we can be quite different again from engineers. And it's a real learning experience as to how best to work together with each other in those settings, which is part of the theme that hopefully will come through in this talk. And along the way also did some incident and accident investigation and actual work following on from that in the Royal Air Force, which is a theme that again will hopefully run through this. So as we are thinking about the human and the systems in aerospace, it's trying to prevent incidents or prevent accidents, and in the context of engineering them into the system or designing them into the system and our interplay with the engineers, it always is having an eye on survival, function, performance, to try and prevent incidents and accidents if we can design them out of the system. And then I spent 4 years working as a consultant at the RAF Centre of Aviation Medicine before retiring from the Royal Air Force to move over to King's, where I am now as head of aerospace medicine, and hoping to pivot from mainly aviation with some space to try and be mainly space with a bit of aviation. And we'll see how that goes and what opportunities we can generate for other people along the way as well. So now on the other side of this, we've got various societies and organisations that I've been involved with, and I would strongly encourage you, as I say, to get involved, volunteer in whatever groups you can, and try and find out what path you would like to be involved in and what opportunities there might be to get experience and exposure along the way. So in the UK, Royal Aeronautical Society, along with the Next Generation of Aerospace Medicine Group, are good ones to be involved in. Looking internationally, the Aerospace Medical Association or the International Association of Aviation and Space Medicine also run a congress, and there's now the European Society of Aerospace Medicine and various others. So there are lots of ways to try and get involved, and if you can go in person at some point, it's a really great way to meet the community and get exposure to find out ways to get involved in the field. And that certainly helped me a lot along the way, and I think you'll find that most people will be very happy to try and help you along on your way as well. And I've done a variety of bits outside of the core aviation and space medicine elements as well. And onto the fun stuff now. So I firmly believe that the operational experience and being in and around these environments ourselves gives us a great footing with which to speak to our patient populations, or to consider the physiology or psychological performance elements a bit better when we have experienced or can appreciate the challenges firsthand of operating in those environments. And then in the context of this talk, that greatly guides what we might do in terms of personal protective equipment, life support systems, or vehicle and habitat design. So I do like to get out and do these things, both from a research setting or just from a personal experience bit. And it is really underpins all that I do. So I do both enjoy doing these things, but also get great professional relevance out of these exposures. And I would encourage you, if you like these kind of things or are interested in the field, to do what you can to see what they're like for yourself as well. And you can normally draw some relevance back to your work or research, clinical aspect, or the engineering side as well. Okay, so in terms of the specialty, I think you've already had a few talks that are starting to paint this picture. I'm not going to be focusing on or talking around the clinical aspects, although clearly they are significant parts of the specialty and what we need to think about. And similarly, human performance, that comes into the physiology and the psychology, and absolutely fundamental to supporting people operating in these environments, both on the clinical and the human performance side. And they're vital to managing the human risk in the system or the mission, which is the core of what we do as a specialty. But I know you've had other talks on those topics. So really, I'm going to focus on the designing the human into the system. So the human factors engineering, as it's labelled on this diagram. And hopefully the other talks have already identified the fact that no one group of people can deal with all of these different aspects of our specialty. And it is very much an interdisciplinary field, and that's one of the things that I really enjoy about it, and I particularly enjoy this interface with the engineers and our international colleagues, because these problems and challenges and solutions tend to be addressed in a multinational way, which is great. And it really is a big team sport that you have to have lots of different backgrounds and specialties involved in. So I'm just talking really today about the medical physiology, a bit of the psychology, human factors, and the engineers, but there are many other people involved as well. So if we delve a little deeper than that top layer of those three areas, it really starts to hopefully give you a framework for what the rest of the talk and the interface with the engineering is. So at the bottom of the screen there, we're thinking about the person, clearly sort of the patient-centered approach. And then how they interact, how they might be affected by the environment, has multiple levels here, from the personal protective equipment, their clothing, the vehicle or the craft, and then the actual environmental exposure itself. And then what they're trying to do in those settings will all interact and change how this might impact on their clinical side, the physiology, the psychology aspects of the performance, or what you might need to design into the system. So there's lots of different elements to consider here, and all of the different scenarios along the right-hand side there. So lots of variables, which makes it interesting, and why there's a great need for our role to help on the human factors engineering to design the human into the system, because we might be affected in many different ways in all of these different scenarios, and you very much need scenario-specific considerations for all of these different aspects. To help guide this through a little bit, we've then got another model that I like to think about here, which feeds into both the clinical and the performance side, but for today, very much important on the engineering side of it as well. So you start here with the physics, the exposure itself, and then how that environmental exposure, be it to altitude or G, or lack of gravity in terms of weightlessness, or various other stresses that you might be exposed to in the aerospace environment, how that affects the physiology, the pathophysiology or clinical implications, and then the performance. And then where we'll focus on more today is how the protection systems might be needed to intervene and mitigate those risks, or avoid those risks and hazards associated with those exposures. So I often come back to this kind of model to think about the different interventions we might use, and then when you've introduced a new engineering system, how that knocks back to affect these interactions, and whether you actually introduce new hazards potentially, as well as mitigating the original intended one. And as I said earlier on, priorities here will be to support and focus on survival, function and performance in these settings. And where aerospace medicine and our research arm can come in is to help to identify some of these effects, or to understand and describe them a bit better, and then to assess potential mitigation or intervention strategies, be the engineering or otherwise. So what do we mean by designing the human into the system? Well, all sorts of different things. Hopefully we're starting to build up a picture here that there are many different aspects to consider when you're trying to design the person into the system. From their interface, from a performance side with the system, to simply just, do they fit in the aircraft or spacecraft or vehicle, whatever it happens to be. What's going to happen in all of those different routine flight scenarios, emergency scenarios? Are these systems going to be required on a daily basis in a routine flight, or are they just an emergency backup system? And there are many different ways in which we might need to feed into those considerations, which will start to build up over the rest of the talk. So to give you an idea of what we're talking about here in terms of different systems we might have, we have a fast jet pilot down at the bottom of the screen here. So they are wearing anti-G trousers, so that's a system designed to help protect them from some of the effects of G forces. They've also got a life jacket on, which might help them in the event of immersion in water. They've also got a helmet that could protect them from impact. It also provides within it hearing protection. It's got vision protection in terms of the visor. It's got a mask hanging off it so that you can supply them with sufficient oxygen at adequate pressure. And then they've got various other straps to help in the event of ejection. And then they've got different survival aids, depending whether they land on sea or water, to help with them. And then all of it has got some kind of fire retardancy and protection. So they're wearing very high-tech solutions to help protect them from a variety of routine or emergency type scenarios they might end up in. This then extends to what the force is that would be tolerable in an ejection scenario, and how might that person need to be designed into, consider their size, weight, shape, function, etc., to go on that ejection seat. Similarly, if they then land in the water, depending on what aircraft type they're in, are they going to be in a small survival raft or a large survival raft? And then what kind of systems do you need to be in there to protect the people? How long are they going to be in there? Do they need water, medication, other survival aids, location aids, etc.? So there's quite a lot of different things you could think about where the human physiology, psychology, or clinical factors and requirements feed into the design of these different systems. And they can go into the specification stage, and leading to the design, or it may be involved in the test and evaluation of the products, or when they're actually released into service, or when things start going wrong in service, and then you need to have in-service modifications. So those aerospace medicine input and engagement and liaison, hopefully close working with the engineers and many other people at all stages of this design and feedback cycle, to try and make sure that the whole variety of human needs in these different scenarios are considered. And then it just keeps going round and round in circles as we get different needs and new systems come in, or changes are required with existing systems. So to give you a little bit more of a picture as to what this means, getting down into a bit more level, it might go down to a paper-based exercise, so just a hypothetical scenario, thinking about, well, what are the considerations, what's previously worked, what's previously not worked, what's caused incidents or accidents, how could we design those things out or specify those things out of the contract to get these things made. It may go through to lab testing, which could just be done with a mechanical breathing simulator, for example, or other uncrewed versions, or it may involve human testing, and so you might have crew lab experiments, and ultimately might go on to aircraft and flight trials. To give you an idea of the great variety of different testing scenarios you might need, here's just a little bit of a list to give you an idea of how many different ways you might need to help test or develop some of these life support or protection systems, or new aircraft, spacecraft, or habitat designs. And this is just a few of them. There are many more as well. So there's quite a lot of elaborate testing that might be needed, that might need to have humans being tested in these different scenarios, as that's going to be the ultimate requirement for the system. And then you might need to do it all in aircraft and flight trials. So to give you an idea, a few examples from when I was working at the RAF Centre of Aviation Medicine, up at the top left, we did a comparison of the thermal protection of survival equipment for winter land or winter sea survival settings. So we did a human-rated trial there to see how effective the protection from the thermal stress was in those different clothing garments. Top middle, we've done a variety of oxygen delivery system tests for fast jets or helicopters, and both in terms of primary protection or the backup oxygen delivery systems as well. And that's often done in the altitude chambers or the hypobaric chambers that you can see at the top right. And there we typically would have the representatives of the organisations or the companies or the engineers working with us to help refine some of the designs and performance of the systems, depending on what we find in the human testing. Carrying on clockwise around the screen, we've then got parachutists, and up to 10, 12, 15,000 feet, depending on the regulatory requirements, they can jump and perform without supplemental oxygen. But if they're going to go above 15 or 18,000 feet, certainly, then they'll need to have supplemental oxygen delivery systems. And where we might need to be involved there is specifying what the breathing patterns of the users are, or advising on what the risk of decompression sickness is, and therefore how long they can be exposed for, or how long they need to have a supply of oxygen to reduce their nitrogen load prior to those altitude exposures. And that then has a knock-on effect for the specification of the oxygen delivery system in terms of how long it can last for and how much oxygen there is in it. And then talked a little bit about flight trials that might be in simulators, or it might be in real aircraft. And the RAF Centre of Aviation Medicine has two of these Hawk aircraft, which are instrumented to permit and have had modifications to some of the life support systems on board, so that they can permit real in-flight physiological and medical studies, which is a great asset and tool to do those studies. And then down at the bottom left, we've got the classic, the venerable centrifuge at Farnborough, which I spent many years working at, but has now been replaced by a much fancier one that I'm sure you've heard about from Joe Britton up at the RAF at Cranwell. Okay, so just go through a few more examples. So if you've got a new aircraft that's coming into service, like this RAF Voyager that was brought in the last few years, you need to start with a kind of task analysis. What's it going to be used for? What are the mission requirements, and therefore what are the people on board going to be exposed to, and what do you need it to be able to do? So key bits here are just passenger movements. It's also going to be air-to-air refueling, but they also wanted to be able to do aeromedical evacuation. And so when you're then designing this aircraft, you need to think about what kind of patients might you move, what kind of medical support might you need, what impact is that going to have on the aircraft design in terms of oxygen supply, or potentially do you need to modify the cabin pressurization schedule to keep them at a lower cabin altitude necessarily than the 6,000 to 8,000 feet that it might normally be. So again, there's that interaction from the specification and the design stage, all driven by the scenario specific requirement. And similarly, another recently introduced aircraft here that was being brought in to do, one of the roles was to do parachute drops. So you need to think about how high do you want them to be able to go? Are you going to design in an oxygen delivery system on board for them to use? And where are they going to exit from the aircraft, and practical considerations around that. So one of the important things you think about in any military parachute operations are the injury risk, and so when you're designing the aircraft, you want to think about whether there's any chance of that in itself increasing the risk of injury to the parachutists. Another relatively recent one is a small training aircraft with the RAF, but it was much more performance-wise capable than the aircraft it was replacing, both in terms of speed, the G that it could pull, and the altitude to which it would go. And so in thinking about this kind of aircraft, you also then need to think about things that the predecessor might not have had. So would you want an ejection seat, anti-G trousers that need an oxygen delivery system? What pilot's going to be wearing? Are they going to have helmets on? Again, do people just fit size-wise into the aircraft? And you need to think about that person from the outset when you're specifying the requirements for the aircraft in that holistic approach to what will they be wearing, what will they be doing, what hazards you're trying to protect them from. Another example here, so military side, they bought a nice business jet here, and we're going to convert it into a rear crew training aircraft. So again, you need a task analysis of what the people on board are going to be doing. So this lovely glass cockpit in the front, which was one of the big drivers for the pilot training, as it's more in line with the future aircraft they'd be going on to, rather than the traditional analog aircraft that they were replacing, which have lots of dials and a very different human machine interface in the cockpit. So this is more like what they'd go on to further down the training pipeline. Again, lots of design considerations there in terms of human performance and interaction with the system, as well as training philosophy and the broader system design in that context, in terms of where you're training people to go in future. In terms of the back, very nice looking business jet here, has clearly been designed for people to get in and around, not a huge amount of space between the seats. And when you then think about it in the military context, you want to wonder about what they're going to be wearing, as well as what they're going to be doing in the back. So you can see from this picture, actually, they've generated more space between the seats, which gives better access between them, although depending on the scenario, the people might be wearing different amounts of clothing or different types of clothing that might impede that. But they've added a lot of technology into the back. So actually, is there sufficient space, and are the lighting conditions okay for people to use these devices, etc. So you want to do a good task analysis to understand what people on board are going to be doing and wearing, to then feed into the support systems. Are you changing the number of passengers that are going to be on board, number of crew working in the back? Are the emergency oxygen systems sufficient for that number of people on board, etc. So there's a lot of interactions. Again, anytime you're changing something, you want to think about the humans that are going to be at the center of this new design. Now, talked earlier about learning from the past in terms of trying to prevent incidents and accidents. And here are just a few examples, and you learn from the successes as well as the failures. And going back to the principles, we want to try and improve survival, function and performance, and we want to prevent further incidents or accidents. And there's always valuable lessons to be learned from these, even within the tragedy. And so drivers from Colombia give indications as to potential future escape or emergency systems. The water leak in the EVA suit was a new unexpected challenge, so that posed engineering problems as well as medical, and it was a life-threatening condition at the time. But what do you need to do in future systems to try and avoid that and improve that? And then the Spaceship Two mid-air breakup, where one of the test pilots died and one survived. How can you try and prevent similar things from recurring in future through analysis of what led to the incidents or the accidents, but then also how the emergency systems and support services worked or didn't work, and whether you need to make any improvements in the broader support systems as well as the mechanical engineering systems themselves. And if you've not looked at it before, I'd strongly encourage you to go and have a play on this interactive website that NASA's got. They've gone through all of the different international instance accidents where things have or haven't worked in the space context. And it really is a valuable insight into what you can learn from the past to inform future design or modification of systems and how to operate successfully. In terms of escape systems on the space side, talked about ejection seats for aircraft before. This is then the rocket escape systems that have been used a couple of times now from the Soyuz launch vehicle, and this is if there's a catastrophic failure in the launch rocket. A small rocket fires the pod off the top to save the crew on board, and that's successfully worked a couple of times now over the last 40 years. Looking to the future, one of the drivers from Colombia was to look at different escape systems should a catastrophic failure occur during re-entry, again like that. And that was one of the drivers for the medical team involved with the Red Bull Stratus skydive from the edge of space, stratospheric skydive. Looking at different options to push the boundaries of what the escape and emergency systems might be able to tolerate in those scenarios. So again, there's lots more to be learned and developed in these areas, which hopefully we'll see advanced over the coming decades. Now, another example, so this was a different project, but again, learning from the past, so and trying to identify lessons from tragedy. So in 2011, a Red Arrows pilot died when they were inadvertently ejected from aircraft, and the emergency system that should have opened the parachute and separated them from their ejection seat so that they would land safely and alive didn't work. It failed to open. It failed to activate properly, and this was due to two errors that had previously been unidentified. So they were considered ghosts in the system. So we've been getting away effectively with these two errors in the system without having caused any fatalities over the previous 30 years. And it led to a variety of changes to address those particular problems, but also a broader step back and think, are there any other ghosts in the system? Are there any other things we've been getting away with, so to speak, over the last number of decades that we aren't aware of? So might these systems also fail in other ways that we're not aware of? And I got involved with the review of the fast jet life support systems, and this was again a great experience to understand similarities and differences and approaches between medicine and engineering, and brought about some recommended training courses and educational opportunities for engineers, but also for us on the medical or physiological side to understand better about what engineers do and how they work. And some of the elements from this also feed into unexplained physiological events, which you have hopefully heard a little bit about, and you probably get other talks on later in this series, but where pilots of the latest generations of fast jets around the world experience symptoms in flight that may or may not have an obvious cause, and has caused some great concern in different parts of the world, and has led to various aircraft being grounded for long periods of time. And that's driven an increasing interest in how we can monitor what's happening to the people on board, and this wearable physiological monitors. So what I was asked to do as part of this project was to tell them about why and how hypoxia, or G, can cause people to lose consciousness. And then as we had a bit more of a conversation, what they were really interested in is how can the flight environment cause people to have a decrement in performance that might pose a risk to life, so that could lead to incidents, accidents, injury or illness. And actually that's much broader than just hypoxia or G, and so I came up with this graphic for them to give them an idea that there's a whole load of things that can affect performance, which may or may not have incapacitation risk, and may or may not just be at the other end, but just distracting and a bit harder to tell exactly what threat to flight safety it might have. And then this was the basis for our analysis of the different scenarios with the life support system, where they would talk through different potential failure modes, and we would work through root cause analysis type approach to describe the specific scenario that the pilot would then be exposed to, and we'd work through what physiological or medical implications that might have for the individual. So where on this figure they might end up, and how much of a threat did that specific failure scenario pose to the individual, which was an interesting different challenge, and useful to learn again about how medicine, physiology, engineers might talk slightly different ways and use different language, and have got slightly different cultural approaches and understanding of these different elements. So it was very useful. And one of the challenges in this scenario is you can get lots of different symptoms in flight, moving on to the unexplained physiological events side of things. And the interest in physiological monitoring is to try and help differentiate between these different causes of similar symptoms in flight. And this will be a continued area where physiology and medicine will need to feed into engineering considerations for future platforms. And there's just lots of overlap here that can be quite difficult to tease out. This next couple of slides will say to highlight that it's not just about us trying to educate engineers about what aerospace medicine can do, but there's also learning that we can bring to physiology or medicine. And this is just one example paper I was involved in. There are many others out there where trying to apply aerospace or aviation or engineering approaches into physiology or medicine, and I think one of the key elements to consider for these are that, again, they need to be done in a scenario specific, considered way, and where things might work in one scenario doesn't mean they will work in other scenarios. And I think that's where some of the challenges have occurred when some elements have been moved from aviation practice to try and go into healthcare and haven't necessarily worked as well as you would have expected. Another example where we're looking at this at the moment is to try and use the bow tie model, which is an engineering approach to manage and assess risk. What they have in the middle is an event occurring, and then you've got the two sides of the bow tie on the left and the right, and you've got the threats that might lead to that event occurring, and then on the far right you've got the consequences and the outcomes of that event occurring. And there are many different controls or mitigations or interventions that might mean a threat is prevented from becoming an event. So that's trying to stop something happening. Or once something happens, you can have controls and mitigations in place that mean it's not a bad outcome and you can mitigate the outcome so it's a better consequence. Now, to put that in the medical context that we're thinking about, the event in the middle could be a pilot incapacitation or a passenger in-flight medical event, or it could be degraded performance in the cockpit. And what we've got on the left here is just a few examples of the kind of threats that might lead to those medical events. And at the far right, the kind of consequences in terms of bad outcomes with death or aircraft crash, all the way through to potential no impact on flight safety and continued flight as normal. And then the various controls or mitigations that could be on the left side to prevent the threats becoming an event, or on the right hand side to prevent the event from having a bad outcome or consequence. So again, that's trying to apply an engineering approach to help us think about what we do in aerospace medicine, and this can then be used to drive research needs in terms of where data are available or aren't available, and ultimately in the engineering side they put numbers to all of these elements, and then they can work out where they need to focus their resources to try and improve flight safety from an engineering evidence-based numbers approach, which we hope to try and use this for on the medical side as well over coming years. Now, looking to the future, I'm going to canter through a few examples here now. So it's going to be a science fiction future in the cockpit with augmented reality and virtual reality and lots of wearable sensors. And there are implications here on the medical selection standards and how the human can perceive or interact with these various new technologies. And that all needs to have some research from the physiology, human factors and medical perspective. To try and understand what it means and how these are actually being used, and if they're useful and they're actually going to add to flight safety and help to prevent incidents or accidents and help to support performance and function in these environments. We're also looking at some great technological advances. So in the UK, there's reaction engines. You've got some quite remarkable technology potentially on the horizon that could allow us to get hypersonic or stratospheric vehicles. So looking potentially at going higher or faster. There are also various civilian commercial transport vehicles that are looking at some of these bits. And as we go into this higher altitude or higher speed setting, it goes beyond what traditional aviation life support systems would be able to protect the individuals for, and goes into more of a territory of space life support systems in some ways, or possibly need to look back to the past to think about some of the protection systems we previously had. So the SR-71 Blackbird was a high altitude, high speed vehicle, and their occupants had to have a full pressure suit, so a space suit to protect them from the environment outside due to the potential altitude, but also the forces on ejection, or in the event of an engine failure, overheating in the cabin while they slowed down to get to a speed that they could survive ejecting at. So we may need to look at some of those again, or possibly different examples where they had ejection capsules in different aircraft types. Again, different scenario specific considerations, but they all need to think about the human at the center of them. Continuing this future-looking scope, we've then got the UK spaceport and the potential space plane operations on the horizon. I was involved with as a medical advisor for this report a number of years ago, and again, part of the considerations are the regulatory framework, the governance and assurance to permit these operations to happen, but they're also the safety cases of the operators, and potentially also the design and performance requirements of the vehicles and the associated life support and emergency systems. So again, just trying to drive in from the outset to consider the human in these design processes. And for suborbital spaceflight, there's been around 25 people that have ever flown these flight profiles at the moment, and the populations that might fly these are likely to be somewhat older and may have comorbidities compared with traditional spaceflight populations. They also are likely to have more like an airline cabin environment, so there'll be a mild degree of hypoxia, and then they'll be exposed to varying degrees of acceleration depending on what platform type they're looking at. And again, we're helping with some of the research on this side, trying to understand some of these physiological and medical challenges for these flight profiles. And as I say, changing populations, so older age populations are likely to go on these suborbital flights, and potentially as we look to the future and space tourism moves into low Earth orbit and perhaps beyond, we'll also have these for more traditional spaceflight profiles as well to consider, and how you then design supporting for these different populations into the system. So we look beyond, we've got low Earth orbit growing commercialization of low Earth orbit, which is great. Many different ways coming over the next few years for getting people into space. Looking to the moon, we've got Lunar Gateway, which will be a space station that will orbit the moon, and that will be a stepping stone to returning humans to the surface of the moon. And all of that is going to be a training ground to test and develop systems to go on to Mars. And there are a great many challenges to think about there, which will all require some physiology and medical knowledge to design the human into the system there. And again, a great interdisciplinary team nature. So the closer to home, European Space Agency will be advertising for new astronauts as of the 31st of March. So that's today for when this goes live. And there's a great emphasis being placed here on diversity and inclusivity, which is great to see. And one element of that is their new para-astronaut project. This may have engineering implications in terms of prosthetics or additional tools to help people with physical disabilities perform in the spaceflight environment, or as we look to future spaceflight endeavours, and we broaden populations that are able to operate, live and work in space, we may need to design better vehicles and habitats that encompass this much broader, diverse populations as we look to enable whole humanity to get into space. And as part of that, will be looking, so we've got the Crew Dragon vehicle up here, and we've got potential lunar habitats and then new spacesuits. We need to be thinking about the diversity of populations from the outset for designing these different systems, and what the human needs might be in the different settings, in the whole breadth of it. On the medical side, NASA have their exploration medical capability, and they use engineering approaches to inform the risk associated with future spaceflight missions, to inform the medical system design and requirements from the outset. And that's again a great example of using engineering principles and approaches to manage the human risk in the system, and to provide an evidence-based source to design the medical support requirements for those missions. Again, changing populations, which is great to see here. We've got the increasing number of women and proportion of women that are being selected in NASA astronaut populations. A barrier within aviation and space is still that a lot of the systems and vehicles are designed based around the size and shape of average 1970s male population. And so one of the bits that we really need to make sure as we go with systems forward is that the designs of the systems from the outset incorporate the whole breadth of the diverse populations we wish to be able to fly in space. And that extends also to the culture, the selection, the training pipelines, to make sure that we aren't putting barriers to inclusivity throughout the whole process. As we go forward to the moon, you can see here again various things that, in terms of tasks and systems that people might be using, from the habitats to the spacesuits and the activities, but also potentially emergency medical systems. So we've got a stretcher being trialed at the bottom right of the screen there. And again, this is where we can learn from the past. So great document here about the medical and other issues that they found during the Apollo missions that are summarized here. And this is being used to inform future medical planning, but also the systems and the spacesuits to try and sign out some of these problems. And I was involved with Ryan Anderton and Bonnie Posselt and this good crew doing a ESA related panel and hypothetical concept project a few years ago, looking both at a short-term mission back to the moon or a lunar base. And again, this comes back to the scenario specific considerations and encompassing the whole breadth of the clinical, the performance and the engineering aspects for it. And you need to think about what the people are doing, the exposures they'll have, and again, from the graphics that you can see here, they'll all all sorts of different tasks that we wouldn't currently think of on the International Space Station, and different habitat requirements, vehicles, spacesuits, which all need to have the human needs fed into the design processes, as well as the test and development and the medical systems to support people operating in those settings. So again, lots of different ways in which you need interaction between aerospace, medicine and engineering. To continue that line a little further, one of the big problems they had on the Apollo mission was the astronauts falling over. There's a potential injury risk with this. There's also potential suit failure, so you could cause damage to the suit such that it loses pressure, and that was the basis for this project that I did with Rich Whittle a few years ago when he was doing his Masters at Cranfield University, and it was looking at a hypothetical concept design project for the event of a catastrophic spacesuit failure. And the design idea is very simple. You've got about 60 to 90 seconds to repressurize them before they start to get permanent neurological damage from the exposure to the vacuum of space. So this was, in a very simple way, a pop-up tent that then pressurized, and it would inflate within that time frame to permit you to move your buddy on the spacewalk into the inflatable pressurized tent so that they could survive to be evacuated back to medical treatment at the base. And then wrapping up shortly, as we look to the future, we're going to see a lot more human robotic co-working. So SpaceBit down at the left is where robots will be pioneering a path for us going forward on the moon and exploring potential lava tubes on the moon for future habitation settings, in a similar way that NASA Perseverance is mapping out and plotting and testing different technologies that might lay the path for future human missions. And then in terms of human robotic co-working, we've also got the Simon artificial intelligence type digital assistant, who is a prototype of what may help future space missions where the crew are required to be much more autonomous, related to time delays and remote working at distance from the Earth. So lots of very interesting elements here. Again, need to think about the human and human needs in all of these elements. Coming full circle back to bring space technology to Earth, as we look to support humans and design and engineer environmental control and life support systems to support life in space, they also often can bring about great benefit to terrestrial populations. So this one example here is looking at a closed water loop. So we're trying to recycle and reuse more water in space. So how do you clean that water? How do you make it safe for human consumption again? This is one of the great challenges that you also face in disaster zones, where clean water can be in very short supply, and so this then provides a modular component that can be shipped to disaster relief operations to help supply clean water and sanitation in those operations back on Earth. Okay, thank you for listening. That was a bit of a run through. So talking about my background, how I got into the specialty, and then focusing within aviation and space medicine on this great scope and fascinating area, I think, at the interface of science, technology, engineering and medicine, to really design humans into the system from the outset to help support their function and performance, and even more fundamentally their survival in these extreme environments that we come across in aviation and space settings. So hopefully that sparked some interest, gave you some ideas, and then a final teaser for you to go away with is whether there's any relevance of this potentially slightly random publication that I was involved in, that I think is quite relevant to potential future space exploration and living in space. Anyway, I look forward to meeting some of you at some point in the future, and please do get in touch if you would like to discuss any of these bits or work with me in future, and we'll see what we can try and do. Thanks.